So with that, I am going to turn it over to Kate Smith. So I'll let you get set up. While I get my introduction. So Kate is a professor of computer science at Northwestern in the Chicago area. And she works on a really wide range of areas related to quantum computing, including system architecture, compiler and optimizations, error mitigation, distributed systems, and like a bunch more. Kate also has experience in industry. She managed the software engineering team at Inflection that was responsible for SuperSec, which is a physics-aware quantum compiler. She also spent time at the University of Chicago as an IBM Chicago Quantum Exchange postdoc, and she had received her PhD from Southern Methodist University. So we're really excited to have her here today. She's going to tell us how to unlock our quantum potential with software and compilers. So thank you.
And thank you to all of the organizers of this workshop. I'm very excited to be here and very excited to be speaking. The programming languages community, I think, is so important to the field of computer science, and I am really excited to start getting more acquainted with those that are thinking about programming languages in the quantum space. So today, this talk is going to be it's going to be a little bit of a mix of things just to make sure that we have everyone on the same page. I do have some kind of background material on quantum computing and how it's different from our classical paradigm, just to make sure that everyone in the room, if we have some folks that are a little new to the quantum space, we can all be on the same page before jumping into a little bit of a history lesson. So a primer on quantum software. It's pretty wild to think that quantum computing is a very emerging space, and within the last 20 years, we had the first emerging quantum programming languages, quantum compilers, quantum software tools, and now you can get a job in programming quantum systems. Like, that's wild. After that, we'll move into the role of quantum compilers. So this is really near and dear to my heart. This is where a lot of my research lies, thinking about ways that we can take abstract quantum programs and make them a reality. Because at the end of the day, when we're thinking about computation, computation must be physical if we're going to get any sort of result from that big, exciting algorithm. And then future directions for the quantum stack. So just kind of thinking about the future, where we are now, where we can go, and then going to touch on some of the research areas that I'm currently involved in. And yeah, we'll conclude with that. So let's dive right in. So why quantum computation? We have the power of high-performance compute at our fingertips, yet that's not enough for these really important problems that we're still faced with. We have a lot of open-ended questions, especially with problems that kind of have this similar structure where we're modeling natural systems, they're modeling these big problems where we have this exponential search space where we're navigating through that to find a potential solution. And quantum computers offer a potential for a solution, and they're theoretically able to accelerate certain types of problems, so select problems, by carefully exploiting superposition, entanglement, and interference. And what this does is, rather than with classical mechanics, we're kind of forced to navigate the surface of a optimization space, we're able to leverage quantum tunneling to help us zoom in on those answers to those really hard problems with those exponential search spaces. And example applications include cryptography, chemistry, material science, just to name a few. But it's a very exciting space. And what gives quantum that edge? Well, it kind of boils down to the fundamental unit we're working with. It's intrinsically different from a classical bit where we have one static value, 0, 1. Here we're working with the potential to have multiple values at once with superpositions. The language of quantum mechanics really does kind of boil down to linear algebra. So we have these really nice representations mathematically for our quantum systems, but we can see we're working with vector spaces, we're working with matrices. They explode quite quickly, and that kind of gives us an appreciation for how we have to work with these systems much differently than our classical systems. A little bit more about superposition, entanglement, interference. These are basically the bread and butter of what gives quantum its edge and its speed up in these really exciting applications. So the ability to have multiple states that you're able to occupy at once. Of course, that disappears upon measurement. Entanglement, this correlation that allows us to, even at very far distances, have the property where one action on one state is, or one piece of information immediately and inherently acts on another. And then interference, where we're able to converge to the solutions we're looking for with these neat tricks like amplitude amplification and all these neat little things that we can do with phase. So some of our exciting quantum algorithms, we have some near-term algorithms that are more amenable to a noisy profile. So those would be our optimization, quantum approximate optimization algorithms, a variational quantum eigensolver to be used for quantum chemistry. And then, of course, for our long-term vision, we're hoping to unlock the potential to implement or access these applications in cryptography with factoring, Grover search, we have HHL, and these are just some. We have the space of developing quantum applications is also a very growing space. And finally, with this fundamental section, we'll kind of wrap up with qubit abstractions. So right now, we're working with these prototype devices, and we're kind of interpreting this one-to-one mapping with physical qubits to logical qubits. So we have these physical qubits that are physically implemented with hardware. So here's an example of a IBM transmon device. So we see that one-to-one mapping. But we also have ions and neutral atoms and photons, a beautiful array of all sorts of different technologies that we can use to encode quantum information. But in the long term, we want to move toward this fault-tolerant model of programming where we have many, many physical qubits acting in unison to smooth out errors and actually encode those logical or virtual qubits within them to implement our computation. So this begs the question of how do we take an abstract algorithm and map it to hardware? And a solution to that would be software. So this is a nice interlude to our primer on quantum software. So at a bird's eye view, we're going to start with the history, the current state of quantum software, before turning the focus on compilation. And compilation being the process of taking an abstract specification or algorithm and mapping it down into machine code that is optimized for a particular piece of hardware. And then after this, we'll kind of move into those future directions for the software stack. So software has been an accelerating tool for the research community and the scientific community ever since the 1950s. We had Fortran. That really let us major steps forward for scientific computing. And then since then, there's just been the doors have just opened up in terms of all these different tools and languages that have emerged to help us make these conceptual algorithms into reality on physical hardware. And at the end of the day, why quantum software? So quantum is emerging technology, and for wider adoption, we need tools that get the people closer to the hardware. There's a huge gap that kind of goes between these conceptual ideas and hardware that exists today, and software will kind of help us close that gap. So the things that quantum software can do for us, at the kind of the compilation example that we'll really be focusing on in this talk, it translates and optimizes information from a high level to a low level executable. But then we also have another nice artifact of software that it gives us a means to come to abstractions that we can all agree on and we can all use to reason about algorithms and verify our logic. And then, of course, even if you're not thinking about the representation and translation of algorithms, there's also a beautiful use of software that allows you to create models to improve our understanding of the quantum space. So QTIP would be an example of that. We use it to better understand our quantum systems, and that helps us move forward to create better devices. And then at the end of the day, we must have, going back to the concept of seeing trends from the classical space, software really does accelerate research. As you make developments in software, you're able to gain new insights, which poses new research questions, and it's rinse and repeat. So discoveries enabled by software, those in turn into more research questions. So The development of quantum programming really started in academia in the 2000s-ish range. And from 2000 to the mid-2010s, we first saw the emergence of these three languages, so QCL, Quantum Computation Language, Quipper, scalability, and they were a really major step forward in the sense that they were able to capture that hybrid aspect of quantum computing. So QCL, just to kind of highlight, it was able to support fundamental traditional programming data types such as ins, booleans, strings, vectors, but it's also able to combine that with these data types that were inherently quantum. So that was something that was very new and allowed us to start thinking about quantum computing in a new abstraction. So QCL introduced the quantum register, and then we move into Quipper. And Quipper is a functional programming language that was implemented in Haskell. That really just accelerated this movement into the quantum programming space because it allowed quantum programming that was scalable. Then from there, we started to see quantum compilers, so scalability, and that was kind of a tool that emerged to take these abstract circuits and transform them to make them machine ready. Once we hit 2010, we started to see these devices go online from various quantum companies, and they had corresponding software stacks that allowed you to interact with the tools and simulators that were put online. So this open source software was really driven by giving access to hardware. And something just to note too, that a lot of these languages that emerged in 2010, they kind of springboarded off of the popularity growth of Python. So that's why you'll see a lot of these 2010 and up to even to today languages are largely Python implementations. So today, like we said earlier, you can even get a job as a quantum software engineer, which is pretty cool for a field that just kind of emerged at the turn of the century. So while Python is still kind of the leader of the pack, we are seeing Julia, Rust, C++ now becoming more popular. And we have all these different packages that are merging for a lot of various tasks. However, all of these different packages, while they kind of do things very well, they're very targeted. They're very strategic in the sense that we have packages for optimization, packages for gate synthesis, packages for verification, simulation, and the list goes on. And I apologize if your favorite programming package is not up here. There's a lot. But it's really quite impressive to see that we went from basically non-existent space in the 90s to so many that exist today. And while this is great progress, we still have a long way to go. Quantum applications have made a lot of progress. We also had a lot of progress in device development, but that middleware is largely absent. We've got these onesie, twosie Python packages or other tools that are out there, but something that unifies them and makes them all accessible is something that is really, really a huge area of research. So work in progress, the quantum software stack. We have I think a lot of y'all have probably seen an image similar to this, but layers, involved in classical computing in the 1950s very much model what we have today in quantum computing. So today, for classical computing, we have algorithms all the way to our hardware, a very well-defined stack, a stack that still has a lot of areas for improvement and optimization, but it's a huge open-ended question in terms of what that's going to look like in the quantum space. We have a lot of research areas that are opening up, but there's a lot more to do, and I think that's exciting. I think that there's a lot of opportunity, especially for multidisciplinary engagement among experts in these different spaces who are expert level in these different layers of the stack to come together in the quantum space and develop this software tool chain. So some examples of software stack research, so device compilation, that's one that we'll kind of dive into a little bit more. Synthesis, programming languages, to kind of come up with ways to define and reason about quantum logic, and I think that's going to be really, really critical as we're kind of in that, at the cusp of accessing quantum error correction. What are those abstractions going to look like, going from the virtual layer in an algorithm to the logical layer in quantum error correction, all the way down to a physical layer. So I'm excited to chat with everyone here about those types of topics. So IR, resource estimation, error management, optimal control. There's so many areas to kind of dive into when it comes to developing this space that's in the middle of this opaque quantum computing software stack. And even if there's not tool chains that are exactly fitting into that software stack, there's a lot of parallel research efforts in quantum software that might not help you get from algorithm to device, but they certainly help us improve our systems and programming. So for example, circuit simulators help us debug, they help us understand our systems better. Device design analysis tools help us learn about the error associated with different devices, noise channels, architectural constraints that we can then turn into specifications that we aim for with quantum error correcting codes. So all of these things, while they don't, fit directly into the pipeline of taking an abstraction and putting it into a executable form, they are kind of tangential parts of the and complementary software tools that are definitely a important part of the quantum software ecosystem. So now that we've kind of given a little primer about quantum software, we're going to dive into a little bit of a deeper study where we look into the role of quantum compilers. So to first go ahead and motivate this work, and when we talk about compilation, we have we do have a nice stack that goes from very abstract definition of a problem. We think about LLVM type architecture. We go into taking our parsing a specification, going into technology independent optimization and representation, technology dependent representations and optimizations, all the way down to machine code that can actually be executed. So right now, especially being cognizant of where we are today, this is going to focus kind of at the lower end of the software stack, where we think about taking technology independent specifications and mapping them down to hardware. Just because this is where, one, a lot of the work that I've done has been in, and two, where a lot of people are really focused now as we kind of get to the point where we're trying to map applications on hardware and especially map error correction onto hardware. So we can really test its limits and see what its frontier is. So with that, quantum hardware today, where are we at? And we've made quite a bit of progress. So we're at the point where we have surpassed the capacity of 1,000 qubits per device, but unfortunately that's not enough. Millions are needed for fault tolerance according to resource estimates for the most high impact problems that we're hoping to reach for. And even if we do have 1,000 qubits available to us, oftentimes we are working with coherence times and error rates that don't allow us to access the full potential of that machine in the sense that we can use all of those qubits in unison. So what are the architectural constraints that we are combating? We are combating error rates, so error rates associated with measurement, with state prep, with gate evolution, coherence times that are limited. So we have this stopwatch that starts as soon as our states are prepped, and we have to really make sure we get everything done before we reach that coherence bound. Limited gate sets, so we might have a very nice, ideal set of entanglers or operators that we're working with in a technology-independent abstraction, but what we see in an algorithm might be very different from what we can physically implement. So thinking about that is a very important aspect of the compilation toolchain. And of course, there's a lot of variation between these technologies seen here. So we've got a variety of different technologies that are kind of at play at the moment. And a lot of these require kind of extreme environments to operate, whether that's low temperature or high isolation. So a lot of different things that we have to consider, and all of these architectural constraints are slightly different from technology to technology. But even if you're thinking about one set technology, there's still a lot of variation on just single devices. So these two IBM devices, for example, took a little screenshot from the IBM Quantum Cloud interface. And even though at the surface level, if you looked at their topology, they look identical, they're the same processor class, but they have a very different heartbeat. You can see that their error metrics are very different, so we have a very different noise landscape going from one device to another. So that, along with this kind of chaotic noise, really does prevent us from implementing circuits that are of modest size on devices that exist today, and one circuit description that might fit for one piece of hardware might not be the best for another. So that is the role of the compiler. We have a lot of constraints that we need to take into consideration whenever we're trying to map an algorithm to a piece of hardware. So the compiler can really play a leading role in helping us do that transformation in an automated manner. So we can take a piece of source code, so an idea, a concept, a algorithm, and then through this transformation, we can make a quantum executable that is in the representation that includes the supported hardware instructions, the rules of the hardware, and any optimization rules that we want to take into consideration. So things that might be particular for a piece of hardware, maybe we have a missing link or a dead qubit, we can take that all into consideration into the rule set that the compiler uses. So motivating quantum research in compilers, so we highlighted that there are architectural constraints, there's reliability constraints, taking this application to machine mapping. So how do we adapt these programs to these inherent properties? And then although we have systems, so we talked about the first in the sense that we have all these constraints that we need to be mindful of. A compiler can help us do that. But there's also this really nice second motivation to dive into compiler research, in the sense that while we are improving our quantum systems, hardware improvements alone to get to the fault-tolerant regime are not going to be at the timescales that we want in order to unlock the full potential of quantum. And that's very much seen for 2-qubit transmons, or the 2-qubit entangling gates on transmons. They've improved substantially every year, but if we were to continue that trend, we wouldn't be able to reach fault-tolerant quantum computation at reasonable timescales. So with that, if we invest in co-design, we are able to potentially accelerate the rate at which we reach these really exciting milestones, in the sense that we can potentially unlock these near-term applications in optimization, chemistry, simulation, and then those fault-tolerant algorithms at an accelerated rate if we are building up our quantum software stacks in lockstep with the developments in hardware. So now we're going to consider a near term, so going back to the image of the workflow for compilation, it really will focus on a near-term compiler pipeline that looks at the bottom end of the stack. But we're going to look at what compilation looks like today with gate decomposition, placement and routing, and low-level optimization. So first, we have to think about whenever we're taking any sort of specification and mapping it into machine code, we need to translate these very complex unitaries into a set of gates that is supported by the end architecture. So we aren't really looking at something too complicated, just a fully gate here. But depending on what gate set we choose, we might have a very different representation for this logical circuit. So this is just kind of implemented with a Qiskit transpiler. A very simple example, kind of like what you could use in a getting started with Qiskit type of tutorial. But what we're doing is we're simply just transpiling this circuit so that we transform that to fully gate into a representation that uses a fixed basis gate set. So here we are allowing the use of a controlled NOT operation. Here we're using an echoed cross-resonance gate. And we see that we get slightly different realizations for this circuit. And of course, we would get even more variation if we invoked more constraints during this transpilation process, such as ones associated with qubit-qubit connectivity, error, and whatnot. But just at the very first level, we have to take a device's native gate set into consideration during the compilation workflow. Then we have to consider placement and routing. As we discussed earlier, every device kind of has a different heartbeat that characterizes it. So here we've got 3 devices that all have pretty different coherence times whenever you look at them over their lifetime. Not just among the qubits on a single device, but going from device to device. So we have noise-aware mapping and placement and routing is very similar to procedures that we do in classical computing. But noise-aware mapping is kind of the state of art that we use to assign a logical qubit to a physical qubit on hardware. And like we said earlier, this is considering a near-term compilation pipeline. So we do have like a 1-to-1 mapping with our physical qubits mapping to a logical qubit. So how do we do this? Well, one, we have to take our first placement. So we want to try to place our qubits on the device such that we have the greatest chance for success. So we want to pick some pretty robust qubits. And then we inject swap operations to try to make the quantum circuit agree with the backend connectivity. So we're going to try to minimize the number of swaps that we inject into the circuit just to make sure that we don't add extra gate error if we don't have to. And then finally, we get to low-level optimization. So there's been a lot of nice work done at the pulse level. So with quantum optimal control, you can tune up gates. And that might be an advantage to you if you are working with a specialized set of operators that are potentially optimized for your application. So here we've got different rules that are kind of very like peephole optimizations, very in-place optimizations where you can shift gates around and that can help you cancel things out at the logical level. But if you kind of dig a little deeper and break abstraction, so typically you will see that gates are tuned up to make a nice set of basis gate sets that are easy to transpile to from the logical level. But if you're able to break abstraction, so let's say we start seeing patterns in our circuit representations and we start grouping these unitaries together, we can potentially create a much more optimized implementation of our circuit, which is seen here when we go from a kind of a in-place substitution of we see a gate, we substitute its pulse level description, but here we tune up specialized gates with optimal control that implement these unitaries that we see frequently within our circuit. So a lot of opportunity for savings. But we have to consider that this low level of optimization soon becomes impractical once we get past like 5 or 10 qubits. So that was a simple compilation pipeline. We take our algorithm, we transform it into a set of gates that agrees with our hardware. We map it to the hardware. We route any connections that we need to make sure that qubits can all communicate effectively. And then finally, we do any low-level optimization that might be available to us. However, this is kind of a very idealistic view of the compilation pipeline. There's a lot of room for optimization because we have these kind of stochastic heuristic means to minimize cost functions, and we have to make sure that whenever we're making these, they are developed in a scalable manner. When we saw a lot of the early work in quantum compilation, a lot of it was based on these optimal optimization techniques or SAT solvers, and those won't scale as we get to larger scale systems. We also have to think about that there might be constraints associated with hardware and applications that might make general techniques not the best solution to move forward with. So for example, there's been work that shows that in a architecture, a heterogeneous gate set might be the best for you. We might want to leverage classical compute along with quantum compute. We might want to implement error suppression with dynamical decoupling. How do we carefully optimize the injection of that so that we don't push the scales and actually inject more error into our computation? How do we leverage these newly developed features of hardware, such as mid-circuit measurement, effectively so that we can trade off circuit widths for depths? And then finally, how do we optimize for the eventual goal of reaching quantum error correction. So we have a lot of work, a lot of mapping work can very much pivot to the fault-tolerant regime, but there's a lot of open-ended questions in terms of how do we optimize, so kind of with our eyes turned towards the surface code, whenever we're thinking about lattice surgery, how do we optimize these operations so that they take up minimal space and time in terms of resources. So we're moving into the final part of the talk. We, after going through kind of a little tutorial on quantum software at a high level, the role of quantum compilers, we're just going to talk a little bit about future directions for the quantum stack. So the future of quantum systems is quite bright. There's a lot of exciting new developments. I'm sure a lot of y'all have seen IBM's development roadmap. We've got a lot of things that are highlighted on the roadmap that talk about different solutions for making larger scale systems with modular architectures, many technologies kind of contributing together in quantum systems. So at the end of the day, these systems are heterogeneous systems. So thinking about putting all these pieces together, it opens up a lot of it opens up a lot of questions in the research space. Then we think about how, at the end of the day, a lot of these systems are going to be accessed remotely through the quantum cloud. So how are we able to access these systems? How are we able to verify the results of our quantum executions? And how are we able to target the best resources that match to our applications of interest? And then, of course, quantum error correction is on the horizon. So when we think about all of these three previous thoughts, we need to consider that quantum error correction will kind of change the way that we compile and we work with these machines, and we need to take into consideration all the classical overheads associated with quantum error correction. But this increases the amount of opportunities for quantum software and scaling through these principles of quantum hardware and software co-design. So we can leverage software, just as we've done up to this point in our near-term systems, to make the most of existing hardware. And then we can also develop tools that help guide the future infrastructure that our quantum systems will have. So some problems that are very exciting and that I'm pretty excited about pursuing in the near term, look into characterization, resource allocation, thinking about how we can interact with heterogeneous compute resources within a quantum space. So I'm not just thinking about different types of qubit technologies. We've seen some interesting, or different types of error correcting codes, for example. We've seen a lot of nice work come out recently talking about how to combine surface code with LDPC codes. I'm thinking about how we can combine quantum technology with classical technology. So how we can optimize both of these systems. And I think that there's many areas and many ways that we can take advantage of expertise from the classical computing space, especially in HPC, and apply that in the quantum space as we develop these solutions. So a lot of that kind of ties into hybrid HPC ecosystem management, and thinking about how, with all of these things, we can, and maybe at the lower level, thinking about how we can continue to make the most of our hardware with these synergistic error management techniques that combine error suppression, mitigation, and correction. So now I'm just going to take a moment to kind of talk about a few projects that I'm currently working on that kind of address the first three here. So there's two projects. The first project looks at system characterization and resource allocation. And the second project kind of dives into more of the details of modularity-aware compilation. So first, this nice little project that looks into dynamic quantum resource allocation through polychecks was guided by the insight that during compilation, we are forced to map specifications to this very chaotic noise profile. That's not only very different as we look across a device, but it's subject to change. And we are dependent, the state-of-art techniques are leveraging characterization data to guide our mapping on hardware. And this presents a problem. We all know drift is a problem in quantum systems, and we all know that as we scale up our systems, how much insight are we going to have to the backend data, or perhaps it's not even complete or up to date. So that creates a lot of challenges for us. And while there's been prior work in terms of implementing these lightweight benchmarks that allow us to learn the error profile of a machine and quickly apply that to compilation, that might have you, that comes at the cost of extra overhead in terms of machine cycles. So that might be a little expensive, especially with quantum hardware being so expensive to access. So we were guided by this new body of work. We've been doing a lot of work with polychecks, and what a polycheck does, it's actually a clever way to leverage a phase kickback in order to do error detection. You can have its polycheck sandwich implementation. You can have an Ancilla-free polycheck, although the Ancilla-free version doesn't allow the benefit of quantum error mitigation. But essentially what it allows you to do is you can surround a payload circuit, and then you can use the syndrome data produced by the polycheck to give you insight to whether or not an error occurred during your computation. But of course, as with any type of optimization technique, there's no free lunch. So you have to kind of determine the right amount of checks to use. So we explored that in polycheck extrapolation. And then you also need to kind of consider if the polychecks, each check will kind of be tapped into different noise channels. So picking the right check for your circuit is also an important problem. So in very small analysis, we kind of started out just seeing what we could do with these polychecks, and we saw that whenever we had a simulated quantum machine kind of booted up with a unknown noise profile, we saw that, as we suspected, that the check counts from our polycheck sandwiches were able to accurately model, and were highly correlated between, there's a high correlation between the noise model of the machine and the percent of shots that were removed because our syndrome measured a 1 and indicating that we had an error that occurred. And when we took that to a real quantum device, we saw that those trends also appeared. So we found that there was a correlation between the polycheck check data and gate error rates, providing insight to the and also to fidelity. So we ran some circuits, checked, kind of looked at the fidelity versus the check counts, and saw that we could navigate a potentially unknown profile of a quantum machine with these check counts. We also checked to see what would happen if we injected polychecks into quantum payloads that were more practical and more kind of like based in reality. And whenever we applied our polycheck techniques to QAOA circuits, we saw fidelity improvements at around 11% on average and up to 33%. So we were pretty pleased with those results. So first we have some work that kind of looks into device characterization and resource allocation. And then in this work, we really look into how to address the problem of modular quantum compilation. So we have a lot of compilers that do exist, some very good compilers that do exist, but they do have their constraints in the sense that they really just target, they're really built for monolithic architectures that maybe have fixed gate sets, and they really don't have cost functions that are easy to tune to modular systems. So because these modular systems are emerging, we're trending towards a multi-chip architecture in the quantum space, but we have these questions, and the biggest question really revolves around how we can adequately map our algorithms to these pieces of hardware in an effective manner. So we were also motivated to see if we could apply the principles of parallelized compilation in the quantum space. So in our work, Stratify, Elaborate, Quantum Compilation, we optimized for modular quantum systems. So we had this two-part process in our pipeline where we had a stratification that splits an algorithm among chiplets based on our cost function that was informed by hardware, and then elaboration compiles all those chiplets in parallel. And we had this added benefit with our compiler that was able to support heterogeneous gate sets and gate sets that were not entirely universal. And why is that important? Well, in some architectures, especially in smaller setups that you might see in an academic environment, a swap operation might not, or a 2-qubit interaction between chiplets might be a swap. It might not be able to implement an entangling operation. So how do you take that into consideration when you're mapping your algorithm? So we had those as leading kind of motivation for the development of our Stratify Elaborate quantum compiler. And what resulted when we took this modular approach to compilation, we saw some pretty nice fidelity improvements on a variety of different benchmarks, and pretty nice reduction in inter-chiplet swaps, which is quite nice whenever you're thinking about the overheads that can be associated with going chip to chip in a quantum system. So with that, I'll go ahead and wrap up. Thank you for allowing me to present a little bit of a tutorial on quantum software, a little bit of a deep dive into quantum compilation, and some of the work that I'm really excited about in the space of quantum software. So if there's any questions, I'd be happy to answer them.
Yeah, thank you so much. Let's. Do you want to run that around questions?
Thanks, Kate. That was great. Is this working? I would like to hear a bit more about this stratification you mentioned at the end. So 2 parts. One, what assumptions do you make or do you need to make about the links between the chiplets? And then roughly, how do you perform stratification?
So this is a work in progress, and at the current kind of the implementation we have, we were very much inspired by different work that's come out of research groups that looked into, like in the academic setting. So we were looking at both like microwave links between separate chips, and then also flip chip architectures. And we had a tunable parameter in terms of like what the error rates would be in our cost function. So we would try to, within the stratification, try to cut our algorithm such that we could cut at a point where the subcircuits would need minimal communication among with the other processors. But it's a very parameterized cost function. But that was the kind of the assumption we took, and we did really focus on superconducting circuit hardware. But the next step is to kind of branch out into other types of qubit technology. Thank you.
Hi, Kate. Thanks for the great talk. I wanted to ask about quantum resource estimation in a hardware-aware world. So today, when algorithm designers want to answer the question of how big of a quantum computer do we need to run some algorithm, they might count the number of qubits, logic gates. They might refine that by computing the footprint of all the magic state factories. But all of that is still pretty hardware unaware, right? We still have to think about connectivity and pulses and all of these things. I was wondering what your thoughts were on how to answer resource estimation questions in a world where we have all of these different hardware-aware compiler techniques.
Honestly, that is such a good question. So I kind of think that the going back to the picture of the big blank space in the quantum software stack, I think that there's been, in the resource estimation front, a lot of progress that's been made. And then in this kind of low level, in between the data and physical layer, optimization and compilation, a lot of work has been done. But I do think there's like a missing abstraction in terms of this concept of we have virtual qubits in our algorithms mapped down to logical qubits, mapped down to physical qubits. There's kind of, I think we need to come up with more compilation strategies and mapping strategies that are going from like that are meant for like lattice surgery, for example, and the operations that are going to be implemented within error correction. So I think those are largely missing. I'm really interested in pursuing research in that space, so potentially we could chat more about that.
Yeah, so thank you very much for the talk. I found it really interesting. I'm curious, so you showed those, going back to when you're talking about the stages of the compilers, you showed these several different stages, and I'm curious what you think about like the both different, ways that you can implement these stages, but also how they might interleave, or if you need to run them multiple times. Like, how do these stages fit together, or are there like diminishing returns, and maybe it doesn't matter from what you've seen?
Yes. I think that it's challenging because sometimes if you venture too far into one abstraction, like pulse level optimization, once you kind of optimize at the pulse level, it can be kind of hard to go back up to the logical level in some cases. So I think to kind of help just improve the interaction between these different tools, adopting more universally an LLVM architecture for any sort of compiler tool, I think is going to be handy to make sure that we can, and there are, movements made in that direction, but I think kind of moving in unison with the development of hardware tools or software tools, I think will be really helpful to make sure that these different optimizations can interface with each other so they can all be used harmoniously rather than have them kind of combat each other and create a less optimized algorithm if one is run after the other. But the chain of optimizations within your compiler pipeline is, optimizing that is a problem in itself. So.
Any last? All right, let's thank Kate again.